Good afternoon, everyone. I'm presenting our work, Come Here or Still Water, Alleviating tail latency in Cloud Block Store. This is joint work between Tsinghua University and Alibaba Cloud. Before the technical content, let me say something about why tail latency really matters here. Cloud block storage is the foundation under almost every cloud workload. Virtual machines, databases, online services, big data jobs all sit on top of it. So when block storage hiccups for 10 or 100 milliseconds, the impact is not abstract. A database transaction stalls, a checkout page times out, a live stream buffers. During shopping festivals like Black Friday, even a small handful of slow requests can affect millions of end users. That's why, for us at Alibaba Cloud, low latency, tail latency in block storage is not a nice to have. It is a hard SLO that we have to meet. Now let me show you the stack we work with. EBS has 3 layers: compute hosts the VMs and the virtual disks. We call them VDs. Each VD is divided into 32 gigabyte segments. The proxy layer in the middle is where the I/O processing happens. Also garbage collection, indexing, scrubbing. The storage the storage layer is a distributed file system similar to HDFS. This is three-layer shape is not unique to Alibaba. AWS EBS, Azure Disk Storage, and Google Persistent Disks all follow the same design. Compute and storage on different machines connected by the data center network. So the lessons we share today apply to any disaggregated block storage stack. The proxy layer on paper is supposed to be small, but spoiler, it is also where the tail latency trouble shows up. Now here is what production actually looks like. This is one of our EBS clusters over a 40-minute window. The dark line is the 5 nines write latency. Most of the time it sits where we want it, but every so often it spikes, and these spikes reach out about 109 milliseconds. We are not cherry picking. Across the 100 wait a moment. So let's look at what one of these spikes actually looks like in production. On the left is the aggregated cluster-wide traffic. You can see a clear burst event. On the right, 9 random proxy nodes from the same cluster, each shown over the exact same time window. Every single one of the 9 has a load spike at the same instant. So bursts are not localized. When the cluster bursts, every proxy bursts together, including the proxies of small, well-behaved customers. The innocent ones get caught too. But this raises an obvious question. How can one event hit every proxy in the cluster at the same time? This is the breakdown of the when the spikes happens. We picked one of these spike events and broke down the 5-9 latency by layer, and the result is striking. Out of the end-to-end latency during the burst, the proxy layer alone accounts for about 3/4 of the total, 74%. So whatever is going wrong, it lives squarely in the proxy. Before we look deeper into the proxy, one obvious counter-argument: we did not ignore load balancing. In production, we balance load at 4 levels, 2 static and 2 reactive. The static ones happens at placement time. A client's VDs are spread across clusters in the same availability zone, and the VD segments are spread across proxies in the cluster. The reactive ones trigger at runtime. When one segment becomes hot, we migrate it to a colder proxy. When a whole cluster is under pressure, we migrate VDs to a colder cluster. And it actually works. Here is the coefficient of variations of intra-cluster request arrivals across proxies. For reads, writes, and all traffic combined over a full day of production data. CV stays between 0.08 and 0.18. By any conventional metric, the load is well distributed. So the puzzle is, if everything looks statistically balanced, where do these spikes come from? The answer is the customer mix. In a typical EBS cluster, the top 3 clients alone owns more than 51% of the VDs and generates about 63% of the traffic. These are the major clients. Larger e-commerce, live streaming, gaming. When one of them runs a flash sales or a live streaming event starts, the burst doesn't just hit one server. Because we already spread their VDs across the whole cluster, that is the load balancing doing its job. The burst now hit many proxies in the cluster at the same time. So load balancing did not contain the burst, it amplifies the blast radius. So what's the obvious fix? We tried 4 and all of them failed. First, hard rate cap on the major clients. But then we waste up to 27% of cluster capacity in the common case. Second, migrate the hot traffic to another cluster. But migration tasks takes about 20 minutes. Bursts last under 1 second. It's far too slow. Third, per VD throttling. That directly hurts the customer's SLA, which is unacceptable. Fourth, react after we observe the burst. By the time we react, the burst is already over. So that closes the burst story. Now, since the proxy was so dominant during the burst, about 3/4 of the latency, we got curious about the underloaded case. So we went back to the same breakdown chart and uncovered its bottom half. Same story, even at a low cluster utilization, the proxy still owns nearly half the latency. So why is the proxy so slow when nothing seems to be happening? The answer is the event loop thread model. Each proxy uses a single FIFO task queue, mixing everything together. In the diagram, the uppercase letters are IO-related tasks. The lowercase letters are everything else: garbage collection, monitoring, dumps, all on the same thread executed in order. So when a heavy lowercase task takes the thread, a fresh IO request waits behind it, even when the cluster has plenty of CPUs. So the obvious fix is to move IO-unrelated tasks to a background thread. We tried it. This is so-called thread splitting. And many tasks do move easily: garbage collection, monitoring, and statistics dumps. But other tasks, such as snapshot and index compaction, have data dependencies on the IO states. They cannot be safely relocated. They have to stay on the main thread where they keep stalling new IOs. So thread splitting alone gets us only about 10% latency improvement. The conclusion: we need to schedule these tasks, not relocate them. So we have 2 problems on the table: bursts that are caused by major clients, and event loop interference at low load. Before we look at these fixes, let me state the constraints any fix has to satisfy. First, no hardware upgrade. We cannot just throw faster NICs and SSDs at the problem at this scale. Second, no major architectural overhaul. The proxy stack is mature, and a bigger rewrite is too risky for the production. Third, the fix must be effective and fair. It must help during burst without hurting the steady customers, and it must not regress SLOs. So here is the key idea behind the burst fix. The mistake in all the naive approaches we just rejected was that they tried to throttle clients or whole VDs. That is the wrong granularity. Our reframe: don't throttle clients, throttle hot segments, and during the burst, give the steady, well-behaved segments a way to keep serving their I/O while the hot ones are throttled. We throttle the burst, not the cluster. So here is the mechanism. Each proxy server has a single token bucket. We call it the main bucket, refilled every 10 milliseconds at a fixed rate. All segments on that proxy share this one bucket. They compete for tokens to issue their I/O. Now here is the twist. We add a second bucket on the same proxy, the check bucket. It is also per proxy and also shared, but only segments classified as static can withdraw from it. When a hot segment bursts and drains the main bucket, the hot segment cannot dip into the check bucket. Only the steady segments can. So during a burst, the hot segment naturally backs off. No main tokens, no check tokens. While the steady segments get extra capacity from the check bucket, exactly when they need it most. So one question that always comes up: how much can steady segments safely overdraw without pushing the proxy into the danger zone? We answer it with a small MM1 queuing model. Equation 1 gives the expected I/O latency at the target tail latency. Plugging that into equation 2 estimates the residual available bandwidth, and subtracting a small headroom of about 330 megabytes per second gives the check bucket size. The full derivation is in the paper. Okay, that covers the burst fix. Now to the second fix for the underloaded regime. Two principles, both lightweight. First, prioritize I/O. The event loop should always serve I/O-related tasks before any other task. They never wait behind the tasks like GC or monitoring. Second, prevent starvation. The low priority work still has to run, but bounded, so it cannot push I/O off the deadline. In one sentence, let I/O go first, but don't let the others starve. Here's the mechanism. We split the single queue into two: a high priority queue for the uppercase tasks and a low priority queue for the lowercase ones. 3 rules per loop. One is always serve high priority first. Each loop starts by checking the receive buffer, then drains the I/O queue completely. 2, run low priority for a bounded window we call LT, around 10 milliseconds. 3, this is the anti-starvation key. LT is not a fixed number. It scales with the I/O work just done. LT equals 1.2 times the I/O time with a floor of 10 microseconds. So no matter how busy I/O is, the low priority always gets about 20% of the I/O CPU time and never starves. Now to evaluation. We split it into 2 parts. The first, what happened on a controlled testbed when we play real production traffic, then what we measured after rolling out the mechanism out to the production. For the testbed, 8 compute nodes, 16 storage nodes, we take an actual production burst trace from one of our clusters, exactly the kind of spikes we showed at the start of the talk, and replay it. Without dual bucket throttling, the 5.9 latency on the innocent I/Os during the burst climbs to about 80 milliseconds, and with it, on the same trace, the same innocent I/O drops to around 10 milliseconds. That is about 71% reduction. So replaying a real burst in controlled environment, the mechanism delivers what the design promised. Now to the for the underloaded regime, we played two production traces, one at 200 megabits per second, one at 300. These are typical average cluster throughput levels under normal non-burst load. With the priority-based scheduler enabled, write 5 nines latency drops by 13 and 14% across the two traces. Smaller than the burst gains, but consistent across both traffic levels, and it comes from a single scheduling changes, not a hardware swap. Now to part 2. What happens after we roll the mechanism out to real production? Both fixes have been deployed across dozens of EBS clusters, multiple availability zones, hundreds of proxy servers serving hundreds of trillions of I/O requests for over more than half years. Here is the representative burst events observed at the same time of day across several consecutive weeks. With dual bucket throttling enabled, the 5 nines tail latency on the steady segments dropped by about 59.7%. So the trace replay number 71% translates into about 60% in massive real-world production. For the underloaded regime in production, we ran a week-long A/B test inside a cluster. Single cluster, 2 proxy nodes, same cluster, same workload, one with the priority-based scheduler enabled, one without. Before the changes, their latency curves almost overlap. The moment we enable the scheduler, the vertical dashed lines on the chart, the test node, the 5 nines latency drops by about 22% and stays there for the rest of the week. Interestingly, this is larger than the trace replay number, which makes sense. Real workload contains more I/O unrelated tasks than our replays do. So to warm up, 3 goals, 3 benchmarks. 1, all fixes are software only, no hardware upgrade. 2, no architectural overhaul, just 1 extra bucket per proxy plus a queue split. 3, the mechanisms are validated in production, 59.7% burst latency reduction, 22% at a steady load with innocent customers protected. Thank you. The traces are publicly available on Tianqi.